In this lecture, we will discuss the Cacti tool, which is used to model caches, and we will also discuss the Elmore delay model that is used by the Cacti tool to model timing and power. So let us start by asking a simple question. Any architect will always be confounded with such dilemmas. For example, should I use a 4 KB two-way associative cache or an 8 KB one-way associative cache, right? So well, then this is not a very clear-cut question, right? Well, it doesn't have a clear-cut answer. The reason is it could be that the access time of this is 2 cycles and the access time of this is 1 cycle, right? Because it has a lower associativity. It could be the reverse. Furthermore, the miss rates could also be different. Hence, unless we perform a thorough simulation where we find out the access times of these two designs and then we simulate them for a large number of workloads, we will not be in a position to say which design is actually better, because they are sort of in the same range, and without a lot of simulation studies, it is hard to say which one is better. But what we definitely do need is, given the design of a cache, we should be in a position to find out how long it takes to access for a read and write, and secondly, what is the average power dissipation, how much energy is required for making a single access. The other important question is, how many concurrent accesses should we allow? Should we allow 1 access per cycle? Should we allow 2 accesses per cycle? Right? And so this of course has a cost, in the sense if we have a multi-issue pipeline, then having multiple accesses per cycle is a good idea. Alright. But this has a cost. So we will see what is the cost and how to do it, because the SRAM array that we have presented allows a single access, right? It doesn't allow concurrent accesses, so we need to do something more. We'll see what we need to do. But what we need to do is that the basic 3 steps have to be understood first before we go into more advanced designs. And the 3 basic steps are that we need to find the access times. Of course, under a model of how many accesses we will allow per cycle, 1 or 2. The access time will then be converted to clock cycles. Then we perform detailed architectural simulations of both the configurations, and then we find the faster one, right? Whichever one is faster, that design is chosen. So the Cacti tool, which was designed by HP Labs, it's very popular. It used to have a web interface at least till 2 years ago, but now the tool is freely downloadable. It can be downloaded and modified. So this will tell us the access time, the timing, power and area. Essentially it gives 3 statistics, and so the latest version will also give leakage power. So in chapter 11 we will discuss what leakage power is. But for the time being, let us say that it is the static power dissipation, which is the power consumed even though there is no active access, right? So to actually model a cache and see how long it takes, we need to see how it is constructed. So we will actually find that it is at its heart, at its core, an optimization problem, right? So we need to solve an optimization problem. We can either use brute force, that's a bad idea. So what I would suggest is that you should devise AI based techniques to actually solve the problem. So I'll discuss what are the knobs, what is the optimization problem like, and how it can be solved with AI based techniques, right? So you never thought that you can use AI to design a cache. It turns out that you can. So first let us look at how to do multiple concurrent accesses. So one simple solution, one simple idea which will work in a sense and not work in a sense. So it will work from an electrical sense, it will work, but from a computer architecture sense it's a bad idea, which is that we modify the basic SRAM cell. So the inverter pair is over here. So the basic SRAM cell that has 6 transistors would have consisted of this inverter pair, this word line transistor and this word line transistor. What we do is that we add 2 additional transistors, which means we add an additional word line 1 and word line 2. And along with that we add 2 additional access transistors and 2 more bit lines. So one more bit line pair basically. So we have 2 bit line pairs and we have 2 word lines. See, we do this for every single cell in the array, right? So basically in the entire array what we do is that we have 2 decoders, right? So we have a decoder 1 and we have a decoder 2. Decoder 1 drives the word line 1. Decoder 2 drives the word line 2 for every cell. So it is possible to in parallel access 2 different rows of the SRAM array. So we can still access the same row, but we can access 2 different rows because the first row we can activate word line 1 and bit line pair 1. So then we can read or write this row. And the second row we can do the same. We can activate word line 2 and bit line pair 2 and we can access that row. So let's say it is one row is this one and the other row is this one. So this one can, so the top one can use word line 1 bit line pair 1 and the bottom row can use word line 2 and bit line pair 2. So as far as we are concerned, they are separate accesses because they have their separate word lines and bit lines, and we can have concurrent accesses in this way. So in this case the SRAM actually has 2 ports. Each port allows a read or a write. So we say we have 2 read-write ports, right? So we say we have 2 read-write ports. We can instead design the SRAM in such a way that we have 1 read-write port and just 1 read port. So the other read port will not have a write driver, will not have the facility for writing, but it will have the facility for reading. Similarly, we can say that look, instead of a generic read-write port, we can have just a read port or just a write port. So this will reduce the amount of hardware, but its architectural implication needs to be understood. So what we need to understand is that we need to solve an optimization problem. So there is a trade-off, right? So that wherever there is a trade-off, there is an optimization problem at its heart. So let us understand what is good and bad about the design. So let us consider this design that we have an option. Either we have an SRAM cell with 6 transistors that allows a single access per cycle, or we have an SRAM cell with, as you can see, 8 transistors that allows 2 accesses per cycle. So we will see whether these are read-write or just read, just write. That's a later decision. But the important point is that since we are doubling the number of word lines and we are doubling the number of bit lines, what actually happens when we lay out this circuit is that the area of the circuit will increase by 4 times. Because the y-axis is, having double the number of word lines, and the x-axis is also having double the number of bit lines intersecting it, and because we need to maintain a minimum distance between 2 bit lines known as the pitch, so it will turn out that the area will increase by roughly 4 times. So on similar lines, if we have k ports, right, the port is an interface for a read or write. If you have k ports, the area will increase k square times. So of course one of the negative factors is the additional area. Right, so we of course need more area for the transistors, but the more important thing is we need more area for the wires, and the latter dominates. The other thing is, of course, this is slower, right, slower and more power, because it's a bigger the circuit, more power. So these are all negative. But the positive is that it allows concurrent accesses. So let's say it allows parallel. That's the big positive over here, that it does allow parallel accesses. Alright. So this can be used to increase our IPC, because let's say that 1 in 3 instructions is a memory instruction and we are issuing 6 instructions per cycle. We expect to have 2 memory instructions. In that case, our IPC will undoubtedly increase. So of course here the question is that can we do 2 read-write ports, or just 1 read-write and 1 read, or 1 read-write and 1 write, right? So of course there will pay an area penalty, but we can slightly reduce the amount of hardware. There are a lot of choices. How do we resolve them? Well, so the gold standard is we do architectural simulation, where we take a wide variety of programs and we just simulate the different configurations. And of course we analyze all the data, so we decide complicated trade-offs. That's actually the job of a computer architect, that different sides pull him from different directions. So somebody might be saying that, look, let's have a bigger cache with cells like this that allow multiple ports. Others would say that, look, we don't have enough area for the cache, right? So keep the cache as small as possible, because we need to fit other elements on the chip. So there is a lot of push and pull. So this creates a very fertile space for trade-offs and optimizations. But the main problem, one reason why such designs didn't really take off, right, is mainly because if we increase the number of ports k times, the area increases k square times. So ultimately the area becomes the most dominating concern, right? So we will look at how it is done, how this problem is solved in a slightly different manner. And for that we will have to go through details of the Cacti tool, and then of course I will discuss the optimizations that are involved. So the Cacti tool famously takes 3 inputs primarily. They are called the ABC inputs. So the order in which they are given to the tool is reversed: C, B and A. C is the cache size in bytes, B is the block size in bytes, and A is the associativity. So then there is another parameter that can be provided. It is the number of banks. For a bank we can think of as a sub cache, but we'll discuss more later. And there are 2 more inputs which are hidden, but you can always change the code of Cacti and change them. So one is that what is the output width, in the sense how many bits or bytes do we read out in one go. So it could be 4 bytes, could be 8 bytes, can be configured. And the other is what is the width of the memory address. So that can also be 4 bytes or 8 bytes, 32 or 64 bits, again can be configured. So we give it the inputs and the output. So the inputs are just ABC inputs with a few implicit ones, and the output is of course the area, timing and power. But of course there are many ways of physically designing the cache, as we shall see. So Cacti will choose the most optimal design based on what you tell it to optimize it for: minimum area, minimum time, minimum power, any combination thereof. And then it will give you the specs of the final design. So Cacti is both a estimator of area, time and power, as well as it also computes the most optimal design of the cache given your parameters. So a sample input output of how it works. So we provide the cache size over here in bytes. It's a 16 KB cache. Line size, the block size is 64 bytes. The associativity is 4. Maybe you can't see that. 4 is written. The number of banks, well, we will take a look at the bank issue later, but let's assume it's 1 for now. And the technology node, that's very important. The technology node here is set to 32 nanometers. So as you know, every 1 to 2 years, used to be 1 is 2 now, the technology node reduces by a square root of 2, a factor of square root of 2. So given that each dimension reduces by square root of 2, the area of a transistor reduces by a factor of half. So this is how the technology nodes have been progressing. We are currently at 7. So what is the technology node? Well, the technology node or the feature size is the minimum, is the size of the smallest structure that can be fabricated on silicon reliably. So traditionally it is the DRAM half pitch. So well, when we discuss DRAM, I can tell you more about what is DRAM half pitch, and that's going to come in chapter 10. But essentially, if let's say what happens is that in DRAM we have pretty much a single capacitor like this. So if you have, let's say, these parallel copper wires primarily, right, with MOS based capacitors. So the pitch is essentially the distance between two parallel wires, and half pitch is half of that. So the output is shown over here. So the output shows the input first, the number of banks, cache size, size in bytes. It computes the number of sets and so on. And of course the read ports, write ports. So we have a single read-write port. So Cacti also has an advanced interface where these things can be configured. So the most important output is the access time, which is 0.61 nanoseconds. And then a couple of more energy and power and area statistics. So the area is 0.326 mm square. Alright. So most tools like Cacti will maybe end at 32 nanometers, but if we want to use it for 7 nanometers, then we apply what are called scaling rules that take this data that Cacti has produced and multiply them with a set of well accepted factors, derived empirically of course, such that these values can be scaled to, let's say, a 7 nanometer process. Alright, a 7 nanometer feature size. So you will find a lot of IEEE papers that have different scaling rules. Some of the papers are well accepted. Any of those scaling rules can be used to convert numbers generated for a 32 nanometer technology to, let's say, a 10 or 7 nanometer technology. Alright, so how does Cacti work? Well, as we have discussed, given the inputs, it tries to create the most optimal design. So what can happen? Well, if you don't create an optimal design, you will come up with bad designs like this, where it can be very long, let's say, in one axis. One problem is physically constructing such a cache is hard because you will have to unnecessarily displace other elements in the chip, and it just might be very hard to place it. Alright, so just its placement will become very hard. And also, if you have too many rows and too few columns, your row decoder will become huge and very slow. Similarly, if I have my caches like this, well, first, it will be hard to place. Second, we'll have too many columns, so the column mux, demux will become very slow. Alright. So a fast design is typically squarish. It's not fully squarish, but typically looks somewhat like a square, right? Subject to optimization, of course. So how do we do it, right? So here is the idea that how do we actually design a cache, right? What exactly are the steps, the optimization processes? So let me now talk about the broad space of optimization. So what are our inputs? The input is the cache size in bytes, block size in bytes, and the associativity. So from this, we can calculate a couple of things, right? So we can actually calculate everything, and we also know the memory address and all of that. So we know the number of bytes we want to read out, and let's call it B in or B width, which is the size of the input address. So on the basis of that, we can say that the number of blocks in the cache is equal to C by B, right? The number of sets in the cache is equal to the number of blocks divided by the associativity, of course. Alright. And then what we can do is that the first question that needs to be answered is we need to find out the aspect ratio of the cache, where we can say the aspect ratio is, let's say, the height divided by the width. Right? So the aspect ratio so when we buy a TV, right? So let's define it the width divided by the height, because that is traditionally the way that it is used. So the aspect ratio basically says whether the cache looks like this or the cache is squarish, because as you can see the aspect ratios are different. So in a square the aspect ratio will be 1. So we need to figure out what is the width by height, right? So this in itself is a hard thing to figure out, but let us say this is one of the parameters that we will optimize. So let us say that let this be the parameter, let's say NSPD for the data array, D for the data array, sets per row of the data array, right? Let that be SPD. So let this be a parameter. So if this is a parameter, say every row of, let's say, the data array will have n SPD sets. So if it has n SPD sets, it will have, multiplied by the associativity, these many blocks. Then let us multiply it by the block size, these many bytes, multiplied by 8, these many bits. So it will essentially have these many columns. Alright? Okay? So this is clear that NSPD is the number of sets per row multiplied with the number of blocks per set multiplied with the number of bytes per block multiplied with the number of bits per byte. So we will have these many columns. Now the next question is to figure out the number of rows. So the number of rows is not hard to find. So the number of rows, so this is number of columns, right? So the number of rows is basically equal to the number of sets divided by the number of sets per row. So to check that the product is correct, all that we have to do is we will have to multiply both, and the final result is C into 8, which is C into 8 bits. Alright, so this is equal to the number of rows. So this is one of the parameters that our optimizer needs to find out, that what is NSPD. So in earlier versions of Cacti, this had to be an integer, but now even fractional values are allowed, which means that part of a set can be in one row and the other part can be in the next row. So this will clearly give us the aspect ratio of the cache, that whether it is more rectangular, whether it is squarish, it will clearly tell us. Once, so this is an unknown, okay, this needs to be found out. So once, let's say that, we know this, then what? Then what we will have is that we will have a large array where we know the number of rows, where we know the number of columns. But the problem with such large arrays is that they are very slow to access. Why are they slow to access? Bit lines are very long, word lines are very long. So the signal propagation time on the bit and word lines is very high. If there are many rows, the decoder needs to be very big. Many columns, the column mux demux has to be very big. So what we can do is we can partition this big array into several sub-arrays. So what I have done is that I have partitioned it on the vertical axis basically, right? So I have essentially partitioned it. Then again I can partition it this way, right? This is like a horizontal partition. So what I have done is that I have partitioned it into 16 sub-arrays. Alright. For each sub-array contains a part of the data. So we can of course partition it in different ways, but let us say that each sub-array in this case, so let's start with a simple design. Let us start with a simple two-level hierarchy, and later on I'll break some of these assumptions. So let's say a simple two-level hierarchy has an array, okay, and a subarray. So let us say that a block is entirely contained in a subarray. Then there is absolutely no problem. What we need to do is that we are essentially breaking a big cache into like this this big SRAM array into these 16 mini arrays, so to speak, right? And these 16 mini arrays, where each one of them is called a subarray, contains a block. So what we do is we go there and we read it. So what is the time that is required? Well, the time that is required is that first we need to figure out in which of these subarrays the block resides. So let's say if there are 16 of those, so we will need some sort of a circuit to figure out where we need to go. So this will essentially be a circuit that uses a decoder, where we'll use some of the address bits, and then we will find out where we exactly need to go, which specific subarray we need to access. So we go to that subarray, right? And then we read in the block from there. And so since this is a smaller subarray, right, smaller than the entire array, its access time is expected to be faster. So let us now draw a simple trade-off graph. So on one side, we have the access time of the entire array, right? We need to compare that with, let's say, the time required for finding out which subarray, right? And then routing the address bits to that. So this will require a demultiplexer. So let us say that this is broadly decoding and routing. So you need to find out which subarray to go to and send the address bits over there. This is this overhead plus the access time of the subarray, right? So this is essentially the trade-off that we are looking at. We cannot have too many subarrays, like we cannot have 100 subarrays, right? Maybe we can't have 1,000. Number one, because this overhead will become too much. And number two is that now a block will be split across subarrays, so we need to read multiple subarrays, right? Because each one of them would be containing a part of a block, right? So even if, let's say, we are reading not a full block, we typically don't read 64 bytes. But let's say even if we are reading 4 bytes or 8 bytes, even that needs to come from a single subarray, all right? And if that's not the case, then multiple accesses need to be made. So all of this has to be kept into account. But pretty much, subarrays don't come for free. Subarrays have a decoding and there is a decoding and routing overhead. And also the additional wires are required. And each subarray also has its own logic. So they don't come for free. But keeping these costs in mind, we need to basically see whether we have the original array or whether we split it. So large arrays are typically split into smaller subarrays, and that would make it a two-level hierarchy. Alright. So fine, the two-level hierarchy makes sense, and this is what Cacti used to do for a long time. Now of course things have changed and things have moved towards a multi-level hierarchy. Alright, so let me at least describe some slides of the two-level hierarchy, and then I'll come to the multi-level. So as I have described, let me just go back to the two-level part. So the number of sets that are mapped to a word line in this case is NSPD, as we said. Higher NSPD, there are issues. Lower NSPD, there are issues. So we are basically changing the aspect ratio of the cache. When we create subarrays, let's say we have n DWL vertical cut lines, vertical partitions, and n DBL horizontal partitions. So total number of subarrays we create is this much. N DWL. WL is for word line, BL is for bit line, D is for data array. So similarly, we'll have T for tag array like N TWL and so on. So pretty much our optimizer needs to find these three parameters if you are doing a two-level partition. All right. So it's a three-dimensional optimization. So just to tell you, when the bit lines are being snapped, we just snap. So in this case, NDBL is equal to 4 because as you can see, we make 4 partitions. All right. And each of these rows, it contains NSPD times A times B bytes. NDWL is where we do snap on the word lines. So here again we create 4 partitions, 1, 2, 3 and 4. So then we create 4 partitions and we make 16 subarrays. So in the early versions of Cacti, each subarray used to have its own decoder, its own sense amplifier. It was a separate kind of a mini cache on its own, but this idea has changed, right? As we will see, current cache designs don't use this, so they don't use a two-level hierarchy. So current cache designs are smarter. So what they do is that they use a multi-level hierarchy. So a large cache is split into multiple banks. Right? So I shouldn't be using the word cache. To be more accurate, it is much better to say that a large array is split into multiple banks. A bank is pretty much an independent array, right? So a bank is an independent array. It has its own address and data lines and of course its own circuitry. Here is the wonderful idea. The idea is that they do allow concurrent access, right? So basically one is that because they are smaller, they are faster. But that's not the key point. The key point is we can access different banks in parallel. So what do? We take the address. From the physical address, we find the block address. From the block address, let's say we take the 2 LSB bits. We use them to find the ID of the bank. And the address is sent over there. So as long as 2 addresses don't map to the same bank, which is also called a bank conflict, as long as there is no bank conflict, we can support 4 parallel accesses very easily. Alright. So this is, of course, bank conflicts is an issue, but let's say that there is a 3/4 chance of not having a bank conflict. In this case, parallel accesses can be supported rather easily, and this is an advantage of the multi-banked design, where essentially a large array is just split into 4 smaller arrays. Of course, there is a disadvantage, as we have talked about, more area, routing overhead, decoding overhead. There are disadvantages, right? Now what do we do for a bank? So what did we do? So a large array, well, we are not happy with that. We made 4 banks. Banks gave us 2 advantages at the same time. They are faster, but the bigger thing is that they allow parallel access. So that solved our problem. So then what we do, so in this, this is easy. So deciding the number of banks is purely based on how many parallel accesses we would like to support. So let's say that we can have 8 banks. Well, we just take out 3 bits from the block address and just have 8 banks, right? So we have still not designed them. Now each bank needs to be designed by Cacti, and this is what needs to be broken into the subarrays. So a bank in this case is an array, and each of the banks need to be broken into subarrays. So we need to compute these 3 parameters, and since all the banks have the same size, that's most often the case. If we optimize one bank, we optimize all, which means that for each bank we need to compute these 3 parameters. Computing these parameters can be done by brute force, in the sense you consider all possible values, which is what Cacti does. Not a good idea. So this is slow, right? Very slow. What you should do is that you should use an AI based heuristic, right, to quickly find out the combination of these 3 values that gives you the best value of the objective function. The objective function could be minimum time, could be minimum area, minimum power, or any combination thereof, right? That should be done. Now what do we do? What we do is, here is the fun part. Let me go back to our the bamboo paper software that I use, and then I will show you what exactly I intend to say in this slide. So this slide is very loaded. So now we are talking of a multi-level hierarchy. So we are talking of a single bank, and let's say we have computed NSPD, NDWL, and DPL. So we have essentially broken it into a large number of small sub-arrays, right? So the question is that how do we organize them? One simple organization would be that we just break a bank into a two-level hierarchy, a bank and a sub-array. But this is typically not what is done. The main reason being that the routing overhead is high, and also modern processors have complex access patterns. So I'll tell you one access pattern which is important, and which is why the cache design needs to be relooked at. So most modern processors, inclusive of Intel and AMD, ARM also has these features, have what are called SSE instruction sets, or broadly speaking SIMD instruction sets, where we read, let's say, an entire block of 512 bits at the same time. How much is 512 bits? 512 bits, just do your math, it's 64 bytes. Alright, 2 raised to the power 6 times 2 raised to the power 3 is 2 raised to the power 9, which is 512. So many do 128, 256 and 512. AVX instruction sets do 512. But it doesn't matter, right? 256, 512, all of them are large numbers as far as we are concerned. So if, let's say, they are read at the same time, we need to bear this in mind that this is done. So we don't always read 4 bytes. So 4 bytes is the case when you are reading an integer. But let's say even we are talking of a 128-bit access, which SSE does allow. Even the earlier MMX instruction set also used to allow. In that case, we actually pack 4 integers, right? So this is a packed instruction format where we are packing 4 instructions. So they are kind of placed side by side, and we read these 128 bits together in one go. The advantage is that we put them into a 128-bit register, and we take another 128-bit register and we add them. So what this does is that this is like a packed addition, in the sense that it adds corresponding integers and the final result is also packed. So this is very good for all AI kind of algorithms, matrix multiplication and so on, in the sense that it is kind of a intra-instruction parallelism, where one add instruction adds 4 pairs of numbers in one go. This is also called SIMD, single instruction multiple data paradigm, and SIMD is heavily used in numerical computing. That is why most modern processors provide instruction sets for SIMD. Hence it is necessary to read large chunks of data in one go from the memory system. So if we bear that in mind, what will happen is that if we break it into very small sub-arrays, it is possible that, let's say, if we want to read 64 bytes, it might be split across multiple sub-arrays. That will cause some problems, right? So this is not easy to manage. Furthermore, from the point of view of power efficiency, we need not have a large routing and decoding logic that you go here and then you finally locate which subarray or which set of subarrays, read them and merge them. That's a lot of work. We should break this into several more levels. So the first level that we have seen, of course, is the entire array. The entire array did not allow parallel access, so banks allowed. Next, what we do is we divide banks into sub-banks. So within a bank, we cannot access different sub-banks in parallel. So let's say we do a horizontal split. Let me change the color if I can. Yes, I can. So let me do a horizontal split over here. Okay. So let's say the top part is sub-bank 1 and the bottom part is sub-bank 2. So then this kind of simplifies the circuit a little bit, in the sense immediately from the address we know where to go. Now within a sub-bank, we further divide it. So what Cacti does is that Cacti further divides a sub-bank into mats. Alright. So what is the advantage? The advantage of dividing a sub-bank into mats is like this, that let's say we divide it into 2 mats, right? So consider a sub-bank and let's divide it into 2 mats. What we can do is that let's say we want to do an SSE access and we want to read 64 bytes in one go. One mat can provide 32 bytes and the second mat can provide 32 bytes, and then we can merge them. So here we are essentially having a parallel access and we are splitting a block between the 2 mats. So this is giving us a faster access time because the mats are smaller, and also we have parallel access. In a sense, we have these smaller arrays, we read 32 bytes from each and we merge them, and this is much faster than having a larger array that has 64 bytes stored in one go. Alright. And so basically from an electronics point of view, when you read the Elmore delay model, you will realize that the latency of a wire, like a word line or a bit line, is proportional to the square of the length of the wire. So we typically don't want long word lines and bit lines. That is why we would like to have small arrays, and where small arrays can provide a part of the data and we can merge it. Alright, sounds good. So we then, unfortunately, mats are further divided into our subarrays. So you recall that we had originally divided a bank into a subarray, right? But then we forgot about it. But now the entire picture starts to make sense. So what did we do? Let's start again. We take a bank, we divide it into many small subarrays. We arrange the subarrays broadly into 2 sub-banks or 4 sub-banks. So it depends on how we would like to do. So Cacti of course has some hard-coded values, but in industry they run extensive simulations. Sub-banks are divided into mats, where different mats are activated in parallel and they provide a part of the data if there is a need. And then the mats are divided into the subarrays, which is the ones that we had originally computed from NSPD, NDWL and NDBL. So these subarrays within a mat are also activated in parallel. Same idea. So let's say the mat has to supply 32 bytes. Then each of these subarrays will supply a fourth of it, like 8 bytes each. Okay. Each of them will supply 8 bytes each. So this is also fast. So there is one more thing. So then somebody could easily argue, what was the need for having mats in the first place? Why not have a sub-bank and a subarray? Why did you have a mat? Well, the answer is that different subarrays can actually share resources. So mats didn't share resources, but different subarrays within a mat, so let's say we have 4, they actually can share resources, which will make the design more area efficient. So what is the resource that they can share? They can share the decoder, for example, the row decoder. Sorry, this is meant to look like a D. So the row decoder, what it can do is it can take the address bits and then the decoded outputs, right? So let's say there are k-bit decoded outputs. They can be sent to each of these subarrays within the mat, and the subarrays need not have their own decoders. So we are saving a lot of area over here. So this sharing of resources And even sharing of other circuits and buffers and so on can be done. So the sharing of resources is something that is unique to subarrays within a MAT, but not resources are typically not shared between MATs in the same subbank. Alright. So this is a complicated hierarchy we are looking at. It's not 2 levels, it is 1, 2, 3, 4, 5 levels. But different hierarchies play different roles. The reason we broke it into banks is for parallelism. Right? The reason we broke banks into subbanks is for efficiency. The reason we broke subbanks into MATs is basically because of intra-block parallelism. Intra-block parallelism as well as faster access. And the reason we have different subarrays within a MAT is basically for sharing resources, notably the decoder. Right? So that's the reason we broke it. So if you think about it, this is a complex hierarchy and we have a few more optimization terms. So these things Cacti 6 hardwires but need not be hardwired. So one optimization term is the number of banks. So this would of course require architectural simulations. The number of sub-banks within a bank, right? Number of MATs within a sub-bank, right? And the number of subarrays within a MAT, I mean that's not an optimization term because the number of subarrays is known in advance. It is essentially NDWL times NDBL. Alright? So, if I were to summarize this entire complicated picture, we have a multi-level hierarchy where every hierarchy is made with different things in mind. And if we go back to our PowerPoint, what we see is the same thing that sub-banks do not allow concurrent access. However, a sub-bank stores a full block, but then the MATs and subarrays supply portions of the full block and subarrays share resources. You can see an array, a bank, a sub-bank, a MAT and a subarray. Alright. So this to us is a complicated design of a cache, and as you can see there are many knobs that need to be turned for effectively and efficiently optimizing a cache, and architectural decisions, the pattern of your program etc. play a very strong role. All of these things have to be taken into account while actually designing a cache. It's not simple, and there are complicated computer science problems in simply doing the optimization. It's a multi-level optimization space. Brute force is not a good idea. It is slow. And many a time it is not possible because of the fact that it's so slow. Nevertheless, AI-based heuristics work well, and they have traditionally not been used, but they are increasingly being used in architectural design for solving problems of this kind. The summary of this part, before we move to the Elmore delay part, is that first decide the number of banks, which is parallelism, but for each bank first compute the aspect ratio, then NDW and NDBL, and these three parameters can be used. So essentially these three parameters are what our optimizer has to give. So fine, fair enough. And so then dividing a cache into equal size banks, well, we have to keep in mind the probability of bank conflicts, but a bank will at least allow for parallelism, and each bank is split into a sub-bank, MAT and subarray. And as we have discussed, sub-banks are separate, they do not allow independent accesses, but they still store an entire block. And we have enhanced intra-block parallelism because of MATs and subarrays. And subarrays additionally share resources such as decoders. So given this, we need to now go one more level down and figure out that, let's say, given a subarray, how do we find its timing and power, right? So given this, how do we find its timing and power? So finding the power is simpler given a proper model of the circuit, but the timing is much harder. So we will discuss the Elmore delay model that will teach us how to compute the timing of such complicated circuits. So a few experimental results are due. So let us consider a running example of a two-way associative cache, single bank of course, 64 byte line size, 32 nanometer technology. So let us plot the access time versus the cache size, where the cache size is varying from a few kilobytes till 128 KB. So as you can see, the access time is not really increasing that much. And that is mainly because of our optimizations. Because of the fact that we ultimately end up accessing a small subarray, and the subarray is fast. That is why even if we increase the size, let's say by 64 times, nothing big seems to be happening. Right? The access time is what? Increasing from 0.4243 nanoseconds to 0.55 nanoseconds. And this increase is mainly because of the additional wire routing and decoding overhead of finding the right subarray and merging data and so on. But this is minimal as compared to what you would otherwise expect. And this is only because of the optimizations that Cacti has. In comparison, the area does not increase linearly, it increases superlinearly, as you can see. And the superlinear increase is of course because as we add more subarrays, we add more wires, more decoders, more routing logic. So this increases with the size of the cache. So that is why we see the superlinear increase in the area, right? But we didn't see that with the access time, and you'll also not see that with the power. So even the power that is used, assuming that we have an access every cycle, right, at the maximum frequency, is still going up from 0.15 to 0.25 watts, which is again not much, and this is also because of Cacti's optimizations. Now we will come to the final question of cache design, which is that given a subarray, how do we find the time, area and power, right? So the area is easy to find. The area, we know the area of each transistor, we can multiply, that's easy to find. The power and the timing are the important questions. So the time and power of a subarray, right, howsoever you get it. So essentially we take a large array, then we split, and then we take a small one, we further split. So regardless of that, let's say that we come at this particular subarray, what is the time that is required to access it? How do we compute it? Right? So this will be given to us by the Elmore delay model. So what we can do to compute the delay of a cache, or for that matter any electronic circuit, is that we replace it with a simple model, something that we can actually work with, right? Because a wire or a transistor, these are very complicated things to work with, so we don't really know how to model them quickly, right? We can model them, but modeling them quickly is the issue. So we replace a wire with an equivalent RC model that only consists of resistors and capacitors. So we have resistors. Then so resistor indicates the resistance of a short sequence of the wire. This is the capacitance with respect to ground. The reason being that the wire is a metal conductor, and every metal conductor can accumulate some charge. It's like a parallel plate, and there are a lot of parallel plates in the chip, in the sense there are a lot of other wires. So whenever there is a potential difference across two parallel plates, we essentially have a capacitor. And the way that this is modeled is that this is modeled as a finite capacitance to ground, which you exactly see over here. Again, we consider a small chunk, and we have a capacitance to ground, so on and so forth. So this is the RC model of a wire. Similarly, we can have RC models for a bunch of different elements, such as transistors, sense amplifiers, bit lines, word lines, SRAM cells, everything. So what we will do is we will proceed with two assumptions, that in our circuit we will only consider RC trees. So we all know what is a tree data structure. So in RC tree, is essentially an RC circuit that does not have a cycle. Alright. And so that is number one. And the second is that we never have a cross path, in the sense we have one path and another path reaching it like that. So we don't have this kind of a path. So we will limit our discussion to RC trees. And a tree is the same as the data structure tree. Furthermore, we will consider only only step inputs as voltage sources, which means the voltage abruptly goes from 0 to 1 or falls from 1 to 0. So we will, in our basic model, not consider a gradual transition, right? So this, for example, is not okay for us. So the Elmore delay model for such kind of a voltage source will help us compute the time that is required for, let's say, charging a bit line or changing the state of an SRAM cell or a CAM cell. So let us look at a typical RC circuit, which is also an RC tree, by the way. Note the positions of all the resistors and the capacitors, and also the terminals 0, 1, 2, 3, 4 and 5. So we have voltage source connected, so we will only consider the 1 to 0 transition in this lecture. The 0 to 1 transition is also easy to handle, so that is left as an exercise for the viewers, but we will mainly talk about the 1 to 0 transition. In the 1 to 0 transition, what we need to find is that, let's say if the voltage source was connected, right? So we connect the voltage source and then it suddenly drops from 1 volt to 0 volt. Then what would be the voltage at each of these terminals, right? Particularly the output terminals 3 and 5. That is what we would like to know, right? What it would be across time, over time. So what we do is that we replace all the capacitors. So just go back. We replace all the capacitors with current sources, right? So these capacitors are all replaced with equivalent current sources. Each current source, if you recall your discussion on capacitors, the current that it would actually provide is minus C3 dV3t by dt. So why is this? Well, because Q is equal to Vc dq by dt, which is the current, is essentially C times dV by dt. So the current that C3, for example, will provide, so of course, given that it is flowing in this direction, the minus sign comes down because the voltage is decreasing. So it is minus C3 dV3t by dt. So the aim is to compute the voltage at node Vx at time t. What is the methodology? So what we would like to find is, we would like to find this quantity Vij, which is the voltage at terminal I because of the current source placed at terminal J. Alright. So what we want to do, if you go back to this slide, we would maybe want to find the voltage at terminal I, which is, let's say, V1, because of the current source placed at terminal J, which is, in this case, J is 3. If we add up all the components, so since it's a linear system, superposition holds. So if we add up all the components, we will then get the voltage at terminal 1, which is V1. Right, so V1 we will get it over time as a function of time. So while considering one current source, let us disconnect the rest of the current sources, so replace them by an open circuit. So this is a quintessential method of analyzing such linear systems. So let's say I am interested in V34. So V34, I'll tell you in a second what it is. It is essentially the voltage at terminal 3 because of the contribution of the current source placed over here, right? Because of the current source placed over here, what is the voltage over here? So what will happen is that since we have disconnected the rest of the current sources, all of them will get disconnected. The current here is going to flow this way, this way, this way, and go down to ground. So if the current is here is equal to I, then the voltage will actually be equal to IR1. And since there is no current flow along this route because everything is disconnected, V3 will be equal to I times R1. So this is exactly what we see over here, that the current that flows out of the capacitor, the current source at terminal 4 is given by minus C4 dV44 dt, right? So this is basically the current that flows out of this current source over here, which is this capacitance, divided by the voltage. So this voltage is primarily because of this capacitance by dt. So this is the current that is flowing, this is the current I, and I times R1 is essentially the voltage that will be there at terminal 3 because there is no current flow along this branch. Hence, V34 is equal to minus R1. Why R1? Because R1 is the only resistance from this path to the ground, right? So that is why we will have R1 minus R1 times the current, which is given by this value. So what we can do is we can generalize the circuit. So let us say if you have two terminals I and J, and then of course this stands for an RC circuit, and let's say that we want to find out what will be the effect of a current source placed at J on terminal I. To do that, what we do is that we model the RC tree in this fashion, where of course they will have their separate branches, but at some point they will merge. So let Pij denote the RC circuit in the shared path from 0 to I and 0 to J. So the shared path is actually this path. So this path is shared. So let Pij be the shared path from 0 to I and 0 to J. So then what we can do is we can define the term Rij as the sum of resistances in the shared path, right? So sum of all the resistances that are a part of the shared path. Where does this basic notion of the shared path come from? Well, this will be amply clear if we take a look at this slide, that let's say we were interested in the voltage over here because of the current source placed over here. So then we will have one current that is flowing in this direction because the rest of the currents are disconnected, and then the voltage over here will be I times R1, right? So that will exactly be the same voltage over here because there is no current flow along this branch. And the important point to bear in mind is that the shared path is only this much, and this shared path in this case contains only the resistor R1. Now let me consider one more example. If let us say I want to find the voltage over here because of the current source placed at terminal 2. In this case, the shared path will actually comprise these two resistors R1 and R2. So I will then say that Pij, which is P23, comprising of these two resistors R1 and R2. Alright. So if I were to multiply the current that is emanating out of here I, then the voltage will actually be I times R1 plus R2, which is exactly what that formula with the summation is capturing. And the voltage over here will be the same voltage over here because there is no current flow along this resistor. So if I were to incorporate this formula into the next one, what I can say is Vij is equal to minus Rij, which is again the sum of resistances on the shared path, multiplied with this quantity which we have seen before. This is essentially the amplitude of the current source. Since we have superposition in a linear circuit, we say Vi is equal to sum of Vij's. Why? Because it is essentially the sum of each of the current sources, right? Sum of the effects of each of the current sources. So when I add that, I come up with this formula, which is essentially a generalization of this, minus summation of Rij Cj dVjj by dt. So this formula is relatively hard to compute, right? So if you take a look at this formula, it is not that easy to compute it, and that is why prior to Elmore, so incidentally the Elmore delay model is very old. I believe it was proposed in the late 40s or early 50s, but prior to that it was hard to analyze such kind of circuits. So Elmore made an assumption, so you will find more justifications of the assumption in the book that why this was made, but Elmore's assumption was basically, it's also called the single pole approximation. Right, so the single pole approximation says that let us approximate dVjj by dt is equal to dVi by dt. So this basically says that the rate of fall of the voltage or rise of the voltage is essentially the same across all the terminals, and across all the terminals when we only consider one current source at a time. So it's essentially the same. If I were to put in this assumption, this approximation, then you will see that this formula will certainly become very well behaved. This formula will start looking like this, minus Rij Cj dVi by dt, which is a very simple differential equation. So what I would do is that this summation of summation of j minus Rij Cj, this I will represent by tau y. So tau y is essentially a time constant. So what I will do is that Rij is of course the sum of resistances on the shared path. So for each Cj in the circuit, I can compute this. The summation of this is like a time constant of the entire system. So this differential equation is reasonably easy to solve. So if I solve it and put in the boundary conditions, then the solution will come out to this, where V0 was the voltage before this is before we set it to 0. So we can put t equal to 0 over here, so then Vi will become equal to V0 at t equal to 0. And if we put t equal to infinity over here, then Vi will be equal to 0. So this is essentially the solution of the RC tree. And the solution of the RC tree does rely on the Elmore's approximation to a large extent. And Elmore's approximation again uses this formula over here. Tau y is equal to summation of Rij Cj, which comes out from our basic analysis of the shared path in the tree. The shared path in the tree, just to recall, if let's say this is the tree, and let's assume that every edge has a resistance and a capacitance to ground, right? So if let's say this was the tree and this is essentially the ground node, right? And let's say this is node J and this is node I. So Rij will basically be the sum of resistances of the shared path, which is this. So we can say that we move towards the root, and we will always have, so wherever both of them meet, after that this is the shared path. And if I sum up the resistances in the shared path, right? If I sum up the resistances over this shared path, then I come across, then I come to Rij. And if I sum this up for all the capacitors, then I arrive at the time constant of the entire system. So what did Elmore do? Well, Elmore had nothing to do with caches. Okay, so Elmore, at the time of Elmore, caches had not been invented. Elmore essentially gave a general approximation to solve for the timing of an RC tree. That's all that he did. And once you can solve for the timing of an RC tree, well, then you can use subsequent analysis to find the power that an RC tree would actually consume, and that can be done very easily. But Elmore's main contribution was just to find the time constant of an RC tree. So what are the results that can be derived by using the Elmore delay model? So one of the key important results, so there is an example in the book where this is derived in a great amount of rigor. But essentially the key idea is that if let's say consider a wire, a long wire, like a bit line or a word line, and I'm sorry, I was supposed to represent this with a triangle. I replace this with its equivalent RC circuit. So what I can do is that I need to take a look at the time constant, which, as you have seen over here, is summation of Rij Cj. So I can be the end of the wire. So Rij Cj will basically be, if I consider one capacitor at a time, let's say if it is this capacitor, it is the sum of these resistances. If it is this capacitor, it is sum of these resistances. So if you work it out, we will have a series of the form 1 plus 2 plus 3 all the way till n, which is an order n square term. So that is why the most important result is that the latency of a wire is proportional to the square of its length. Its length. Okay. So the latency of a wire is proportional to the square of its length, and this can be directly derived from the Elmore delay model. Alright. So the Elmore delay model will essentially replace the wire with an RC tree. We know how to analyze RC trees. If we do that, if we consider any capacitor, we'll just sum up the resistances. And if we number the capacitors from 1 to n, then the summation of Rij Cj, for Cj of course is a constant, so it will come out. The summation of Rij will essentially be the baseline resistance R times 1 plus 2, 2 because these 2, 3, 4, 5, 6 up till n. If you are assuming that we divide a wire into n wire segments. So this is clearly n times n plus 1 by 2. We are not interested in the constants. It is order of n square. So this is bad news for us in the sense we should never have long wires in our circuit, because if we double the length of our wire, the latency will increase by 4 times. This result allows us to model long wires like the bit line and the word line very easily. And if we couple this with simple models for the decoder, for the transistors, for the mux, demux and the sense amplifier, which again can be modeled in these simple fashion, we can model a full SRAM bank and as a sequence of simple elements, so we can easily find the time that it will take. And also this analysis will help us find the power as well, in the sense that once we know the time, we will know the individual transitions, so we can model the power as well, and it will be extremely easy to quickly model a large SRAM. So what Cacti does is that whenever we want to, let's say, split an array, we need to compute these 3 quantities, right? So of course then we will split it, and then after a split we can do further splits, right? We are not limited to one split, but we can split it once, and then we can split it once more, and so on, right? So as we had seen, we split an array into a bank into a sub bank, a mat, a sub array, and so on. So it doesn't matter, it can even be a 10 level hierarchy, but essentially at every level this is what we need to compute. And then so this is just a way of splitting, so we keep on splitting. And how do we compute these? Well, what we do is that one is that Cacti adopts a brute force approach, in the sense it looks at all combinations of these and then it essentially chooses the best one. But of course AI based techniques can be used like hill climbing and so on to find the best configuration. So for every configuration we use the Elmore delay model, we find the time. If we want the fastest design, we simply choose the best. Alright, so we have spent a lot of time and effort in going over memory systems and in how to model and design caches. So we'll leave the core electronics part now and we will move to the algorithmic part. So the next 4 sections of this book actually, we will discuss advanced aspects of cache design, a new idea called a trace cache, So it's not that new, but at least it's a very, it's a non-trivial and novel idea which has been adapted in many different settings. And finally, we will discuss prefetching. So next we will get into advanced aspects of cache design and discuss the 6 or 7 most common advanced optimizations.